Welcome to this video on energy stores and energy transfers. This GCSE Physics revision session will cover the fundamental principles of how energy is stored, how it moves, and its importance in physical systems. In this video, we'll follow a revision roadmap. We will discuss the law of conservation of energy, identify the 8 energy stores, explore the 4 transfer pathways, and look at efficiency. First, the law of conservation of energy. It states that energy cannot be created or destroyed, only transferred or transformed. In any closed system, the total amount of energy always remains the same. What is an energy store? Think of it as a container where energy resides within a system until a process moves it elsewhere. We use 8 distinct stores to describe these energy locations. Let's begin our deep dive into the 8 energy stores. Recognizing which store is active in a given physical system is a crucial skill for your exams. The chemical energy store holds energy within the bonds of atoms and molecules. Examples include fuel, food, and batteries. Remember to always specify it as a chemical energy store in your answers. Next is the kinetic energy store, which applies to any moving object. The amount of energy depends on the object's mass and speed. Note that because speed is squared in the formula, doubling it quadruples the energy. Objects raised above a reference point hold energy in the gravitational potential energy store. The amount depends on mass, height, and the strength of the gravitational field. A classic example is a skier on a slope. Elastic potential energy is stored when objects are stretched, compressed, or bent, provided they can return to their original shape. Examples include springs, bows, and elastic bands. The thermal energy store relates to an object's temperature and mass, determined by the random kinetic energy of its particles. Remember, thermal energy is not the same as temperature. It is a measure of total internal energy. Finally, we have the magnetic, electrostatic, and nuclear stores. These are less commonly tested but still important. They involve energy stored by magnetic materials, charged objects, and atomic nuclei respectively. Use this grid as a visual reference to memorize the 8 energy stores. Being able to name the correct store for any given scenario is essential for your exams. Now let's move to Chapter 2, how energy is transferred. Energy is moved between stores through 4 distinct pathways: mechanical, electrical, heating, and radiation. Mechanical transfer occurs when a force acts on an object, resulting in work being done. Examples include pushing or pulling an object, stretching a spring, or lifting a book. Electrical transfer happens when charge flows through a circuit. It's a pathway, not a store. Energy is transferred from a source like a battery to components like bulbs or motors, where it enters other stores. Energy is also transferred by heating when there is a temperature difference. The flow always moves from the hotter region to the cooler one, continuing until they reach thermal equilibrium. Heat transfers in 3 ways: conduction through direct particle contact, convection where warmer fluid rises, and radiation, which involves infrared waves traveling even through a vacuum. Radiation can also transfer energy using electromagnetic waves. This includes visible light from a lamp, infrared radiation from warm objects, and gamma radiation released during radioactive decay. Here is a summary of the 4 transfer pathways. A great exam technique is to always identify which stores are involved and which specific pathway connects them to describe any energy change. Let's trace energy in a simple torch. It begins in the chemical store of the battery, transfers electrically to the bulb, enters the bulb's thermal store, and finally radiates outward. Another classic exam scenario is a falling ball. It starts with gravitational potential energy, which converts to kinetic energy as it falls, and finally transfers to thermal energy upon impact. Moving to Chapter 3, useful versus wasted energy. Not every transfer is helpful. Understanding which part of the energy input is useful and which is wasted is vital for calculating efficiency. Useful energy is the output we actually want from a device. For a motor, that's kinetic energy. For a lamp, it's light. For a boiler, it's the thermal energy in the water. Wasted energy is energy that transfers to an unwanted store. In most devices, this energy ends up in the thermal store of the surroundings. This process is known as dissipation. This table compares common devices. Notice how friction, electrical resistance, and unwanted heat are the main culprits behind wasted energy across various machines. Now for Chapter 4, efficiency. Efficiency measures how effectively a device converts input energy into the intended useful output. It's a key calculation in physics. No device is 100% efficient. Efficiency is calculated as useful output divided by total input. You can express the result as a decimal or a percentage. Here is a worked example. A 500 joule input with a 350 joule useful output results in 0.7 or 70% efficiency. Always remember that efficiency values must stay between 0 and 1. Sankey diagrams are excellent for visualizing these transfers. The arrow width represents the energy amount, with the main path showing useful energy and branching arrows showing waste. Finally, we can improve efficiency by reducing energy waste. Strategies include lubrication to cut friction, thermal insulation to keep heat where it's needed, and using better electrical conductors. Why does wasted energy matter? Primarily for two reasons: environmental impact and economic impact. Wasted energy often means more fuel is burned, leading to higher carbon emissions. And it also translates to higher costs for consumers using less efficient devices. Let's review common exam questions on efficiency. You may be asked to calculate efficiency using energy inputs and outputs, identify the amount of wasted energy, or describe the specific energy transfers occurring within a device like a kettle. Now for some key exam tips. Mastering the terminology and avoiding common pitfalls will help you secure those extra marks. Let's look at how to refine your answers for the best possible results. Precise language is crucial. Avoid vague terms like heat energy or electrical energy. Instead, use the correct store names like thermal energy store or quote chemical energy store. Examiners look for this specific terminology. A common mistake is confusing energy stores with transfer pathways. Remember, stores are where energy is kept, such as the chemical or kinetic store. Pathways, like heating or radiation, are simply the mechanisms that move energy between those stores. When dealing with efficiency, keep three things in mind. Efficiency cannot exceed 100%, so check your values if it does. Always show your full working to earn method marks. Finally, be consistent with your units, whether using energy or power. For the conservation of energy, memorize the standard phrasing: energy cannot be created or destroyed, only transferred or dissipated. Applying this law helps you calculate wasted energy by simply subtracting the useful output from the total energy input. Test your knowledge with these quick-fire questions. Take a moment to think about the energy store in a stretched rubber band, or how to identify efficiency from input and output values. Use this summary chart as your final revision tool. Ensure you can identify an example and a formula for every energy store, and confirm you can name the correct pathway for any device in your practice questions. To wrap up, remember, energy is conserved, there are 8 stores and 4 pathways, and efficiency is simply useful output divided by total input. You've got all the tools you need for your exam. Good luck!